So welcome back to the discussion on time-dependent perturbation theory. Today we'll discuss about the transition probability. So you can recall our discussion. So what we have discussed till now is suppose if you have the Hamiltonian, which is a time-dependent Hamiltonian, can be divided into two part, a free part H0 and a time-dependent part V. Okay, so then the system will have some energy eigenstate, the energy eigenstate of H0, and energy eigenstates I can denote by symbol psi I. Okay, in which the H0 acting on psi I can write some EI get psi I. Okay, suppose psi I are the energy eigenstate, so I can be 1, 2, 3, etc. Okay, in general. So then, if you switch on this perturbation may not be present all the time. The perturbation would be present. It is not equal to zero for some small amount of time, tau, for small time interval, tau, and it is zero otherwise. Okay, so that means the system has some discrete set of energy eigenstate, some E1, E2, E3, E4, etc. Then on switching on this perturbation, what will happen to the state of the system? Okay, the system may undergo a transition. So suppose if the initially system is in the state E2, energy E2, then it may go to some other energy level E4, probably. Okay, so there is a system may change from the state psi2 to the state psi4. So I can find out what's the probability for this transition. Okay, now how to find that probability? Because we know that in case of time-dependent perturbation theory, the time evolution of the system, that is psi of t, in the interaction picture, I can write as ui t comma t0, the psi at t0 in interaction picture. So once you know this ui, it is possible to find uh, the transition probability. Okay. Now UI we already discussed in the last lecture. That is UI in different orders of approximation. You can write in the different ways. In the first order approximation, UI can be written as 1 plus 1 by h cross t0 to t vi t1 dt1 integral. And second order, this is the expression for UI. Okay. Now how will you find the transition probability? So suppose initially the system is in the state psi I for the time being, and I want to know what is the probability to reach a state psi f. So pi to f. So the probability of transition from I to f is very simple. I have to just find the inner product psi f ui dt0 psi I mod square. So if we find this, you can find the probability of transition. Okay. Now, what is UI? So UI is a very big term. You can expand this UI in Dyson series. So this is inner product psi f. UI would be 1 plus 1 by IH cross integral some t0 to t vi t prime dt prime. Okay, if you want to put t1, you can put t1. It's up to you. Plus 1 by IH cross all square integral t0 to t vi at t prime. Then again next integral t0 to t prime vi t double prime, then dt double prime dt prime. Okay, so this entire thing is your ui dt0, then the get psi I mod square. So I can do some simplification. So the first term will be simply the inner product psi f psi I plus the second term would be 1 by IH cross the inner product. Okay, better I can write the integral T0 to T, the inner product psi f vi t prime t prime get psi I dt prime, good, plus next is 1 by IH cross square integral from T0 to T, the inner product psi f vi at t prime, then integral from T0 to T prime vi at t double prime psi I dt double prime dt prime and mod square plus, okay, plus etc mod square. So if you want some simplification, what I can do is I can change my vi in Schrodinger picture to Schrodinger picture. So this vi I can write e raised to I h0 t by h cross v in the Schrodinger picture t prime, then e raised to minus h0 t prime by h cross. So I can replace my the interaction term v from interaction picture to this Schrodinger picture using this transition. Okay, so if that is the case, there will be some changes in this expression. Okay, so better I will copy this term, this entire term to the next page. Okay, so what would be our expression then? So this should be equal to the mod psi f psi I plus 1 by IH cross integral T0 to T psi f e raised to I h0 T by h cross v e raised to minus I h0, okay, this T prime v at T prime by h cross psi I dt prime plus 1 by h cross square integral T0 to T psi f e raised to I h0 T prime by h cross vi, okay, sorry, not v, just v at T prime. Then we'll get another integration. Okay, so better I will put both integration here itself. So T0 to T prime. Then that integration would be e raised to minus I h0 T prime by h cross. And next it would be, okay, there is a small issue. So better I will put an identity here. Then e raised to plus I h0 T double prime by h cross and v t double prime e raised to minus I h0 t double prime by h cross, then psi I plus etc. mod square. Okay, now we have to look at very carefully. This e raised to ih0 t prime by h cross, if it's acting on psi f, what would be the result? So I will write here e raised to I h0 t by h cross act on psi f. So this would give e raised to I ef t by h cross. The reason is this psi f is the eigenstate of h0 with energy ef. So it is the energy eigenstate. Psi f is the energy eigenstate of h0. So therefore, this expression is e raised to ih0 t prime h cross acting on psi f simply gives this exponential. And again, e raised to minus ih0 t prime by h cross acting on psi I will give an exponential term. Okay, so I can replace this operator into some exponential term. Now, in the third term, I have purposefully I have introduced an identity here. So that identity I will be replaced by that identity with sum over psi n psi n. Okay, so this identity can be written as sum over n psi n psi n. Then we will get two inner product here. Okay, so I think I will rewrite it. This term, only this term I will write here. So if you just erase it and rewrite our third term. So the third term can be written as 1 by ih cross square integral t0 to t psi f e raised to ih0 t prime by h cross v h t prime e raised to minus h0 t prime by h cross psi n, then integral t0 to t prime psi n. So the psi n, there should be sum over n here, sum over n. So psi n is 1. Then again the same expression would come here, e raised to I h0 t double prime by h cross v at t double prime e raised to minus I h0 t double prime by h cross psi I. So this is this entire term, third term I can write in this particular way. Okay, now again the action of e raised to ih0 t prime acting on psi f will give an exponential term that would become e raised to I ef t prime by h cross, and similarly here this would give e raised to minus I en t prime by h cross, and so on. Okay, so I can write all this term once again. So the probability of transition from the state I to state f within time t, this can be inner product, the mod square of inner product psi f psi I plus 1 by ih cross. So you will get two exponential term. Okay, so that would be exponential. Just look at here, we'll get e raised to I ef t prime h cross, then e raised to minus I ei t prime h cross. So that would become ef minus ei. So e raised to I ef minus ei t prime by h cross p t prime dt prime, and this would be integral t0 to t. And plus the next term is slightly bigger one, that would be 1 by ih cross square, then there will be sum over all possible states, sum over n, integral t0 to t e raised to I ef minus en by h cross into t prime. Okay, there should be t prime there. Then v at t prime. Then again the next integral t0 to t prime e raised to I en minus ei t double prime by h cross v at t double prime dt double prime dt prime plus etc mod square. Okay, so this is the complete term, the complete probability of the transition. Okay, so within the time t0 to t, what is the probability to reach the system from the state psi I to the state psi f? We can calculate using this expression. Okay, now if the psi f and psi a are different states, so obviously this inner product would be 0. So if psi f, psi a are the eigenstate corresponding to different energy eigenvalue, obviously this inner product would be 0. Okay, now if your interest is to find the probability of transition up to the first order, then we can neglect the third term. Okay, so in the first order approximation, the probability of transition from the state psi I to psi f within the time 0 t0 to t, that is simply equal to mod of 1 by ih cross integral t0 to t e raised to I ef minus ei t prime by h cross and v at t prime. Okay, so sorry, so we have forgotten the inner product here, so there should be inner product at all over the places. So that means there should be an inner product here itself. It should be inner product psi f v t prime psi I dt prime, and here also there must be an inner product. It should be inner product psi f vi t prime then psi n, and here again there should be an inner product. Okay, sorry for the mistake. And it should be psi n v t double prime psi I. Okay, good, plus etc. Okay, so that's it. So then so therefore this should be, so inner product psi f v t prime psi I and dt prime mod square. So if you calculate this expression then obviously we'll get the probability of transition. Now for most of the problem, this first order uh, approximation is enough. So the problem related to the atomic transition and as well as in nuclear physics, the first order perturbation theory is enough to find the transition probability. Okay, so for most of the atomic and nuclear physics, the first order perturbation theory is enough. The first order time dependent perturbation theory is sufficient. Okay, in some cases we may have to go for the second order perturbation theory. Okay, so here the thing is, if you look at this expression, here only thing is we have to find the inner product between the psi f and psi I. So if you want to find the transition probability from I to f, so this the first order term so actually represent the direct transition from I to f. Now, if you look at the second order term, if you are going for second order transition, then there's a two term here from psi I to psi n is first, then psi n to psi n of is second. So that means a system can move from the state psi I to psi f through an intermediate state psi n. So that kind of the possibility comes when you're going for second order second order approximation. Okay, so in case of quantum optics, you might have heard about the two photon process and all. Okay, so that kind of phenomena would happen. The absorption of two photon kind of phenomena would happen if you are going for the second order perturbation theory. Okay, so in the first order perturbation theory, it is just a direct transition. There is no intermediate state. Yeah, but if you go for the second order approximation, then there is also possible that we may get the transition through intermediate state. That is, the system can move from the state psi I to some other intermediate state psi n, then finally it can go to psi f. Okay, so that is the difference. Uh, so today's discussion will stop it here. And in the next class, we'll exactly calculate this transition probability for some examples. So first we'll start with a constant perturbation. So basically, if you strictly speak, the constant perturbation may not come under this time dependent perturbation theory, because constant perturbation is basically a time independent case. But anyhow, we'll just see what would happen if you have a constant perturbation for a small amount of time. Then what would be the probability of the transition, and thereafter we'll discuss for harmonic perturbation. So if the perturbation changes harmonically with the time, what would be the transition probabilities? That is a two example that we'll discuss further, and thereafter we'll go for um, the transition or the perturbation theory while for the interaction of the atom and electromagnetic field. Okay, so we can just summarize what are the things we have discussed today. So today, so basically, what we have calculated the transition probability. That is, if you have a perturbation for a system, perturbation for a small amount of time, then what is the probability of transition from one state to the other? So initially, the Hamiltonian is split into two parts. So H0 plus V of t. H0 is completely solvable. So we know the energy eigenstate of corresponding to H0, and that is in general represented as psi I. So there will be many states with the corresponding a definite energy eigenvalue. Okay, so if the system is in some state, then what is the probability to reach some other state in the presence of perturbation? Okay, so that we can calculate by just taking the inner product between the initial state and final state with this ui. Okay, so from the state I to state f, the transition probability you can calculate the inner product psi f ui psi I. mod square, because the ui gives the time evolution, dynamics of the state in the interaction picture. Okay, so we have just uh, substituted the expression for ui in the in Dyson series. Okay, and we have taken the inner product, so we have done some mathematics here. Okay, and with that mathematics I could be able to get uh, the probability of transition, and it is a big series. It will be have many terms. Now in the first order approximation, what I can do is we can only take the second term, because obviously the first term is 0, and we'll neglect the third term. So the total probability I can write simply like this. Now it uh, is we can try rewrite this final expression in another term using the transition frequency, because this ef minus ei can be written as h cross omega fi. So this omega fi is called a transition frequency. So it is customary to write this entire expression in terms of this omega fi. So because we'll use this omega fi term further in our further discussion. So better what I can write is this: the probability of transition from I to F time t is mod 1 by IH cross integral t0 to t e raised to I omega fi t prime psi f v at t prime psi I dt prime mod square. So okay, so thank you everyone for your patience. So with this, we are stopping our discussion. So in the next class, we can discuss about what is the probability of a transition for constant perturbation.